Background in history and the purpose for the research. I'll be explaining the variables of the equation that I'll be explaining, the method that I utilized, and, well, after the results that I got, future research that needs to be done, and I'll have some acknowledgments after that. So, first of all, we all utilize cell phones, TVs. So, for example, the World Cup from South Africa, that is all signal that gets routed through a satellite. This satellite is in an orbit around the Earth. These are very, well, obviously, we use the internet through the cell phone signal for satellites, and these are very important artifacts in our daily lives, even though we sometimes take it for granted. So, say that in the future, we would like to have more satellites up there, or we would like to be able to track these bodies more accurately, and they're going to be some more of them, and we're going to have to be able to track them accurately and fast, because since the number of them has increased, we need to be able to do it in a rapid manner. So this is the driving force behind my research. Basically, our attempt we're attempting to devise a manner to track bodies in elliptical orbits, so that all of us were able to do it in our home computers with the use of any computational program. So now some history. The three laws of planetary motion were devised in the 17th century by a German mathematician called Johannes Kepler. Basically, the three laws consist of, I'll explain you the three laws. The first one deals with, excuse me, the first one deals with the shape of the orbits. He said that actually the orbits of celestial bodies, that's how they called them back in that time, were actually elliptical instead of circular. The second law actually explains that these orbits, the body orbiting around in these trajectories, would cover equal amounts of areas in equal amounts of time. So, for example, in this figure here, you would see that the time for a body to get from here, from this point to this point, is equal to the time of the body to get from this point to this point, and these areas will be the same. And the third law, I think, it deals with a ratio between the period of the orbits and one of the radius, one of the axes, axi actually, of the trajectories. The equation that I'll be talking about today stems from the second law, the one about the areas. That's why I have this small image here. This equation contains transcendental functions. It contains a sine function. When you have a sine function, or general in a transcendental function in an equation, it makes it kind of hard to solve. So you have to utilize approximations and iteration methods to be able to get an accurate answer. And that's what we're doing pretty much. We're utilizing approximations and iterations to be able to approximate this. And just as a historical note, over more than 350 years already, it is said that every 10 years a major paper covering this topic comes up in the scientific community. So there's been a lot of mathematical work sprouting from this problem. These are the variables. This is the actual equation that I'm going to talk to you about. Uppercase M is the mean anomaly. Uppercase E is the eccentric anomaly. Anomalies doesn't mean the actual word in the English sense, but they mean angles. They're right here in this circle. Eccentric anomaly and mean anomaly. They're simply angles that help us describe the trajectory of these orbits. Then lowercase e is the eccentricity. It's simply eccentricity. You can think of it as how much an ellipse deviates from a circle. So, for example, eccentricity can only go from 0 to 1. An eccentricity of 0 means it's a circle. An eccentricity of 1 would mean that it's completely, deviates from a circle. And here we can see an image, as I showed you, of an ellipse, and we can compare it to that circle that is described in. So as I spoke to you about, many methods have been found. They are very accurate, but many of them require very powerful computers to be able to do them. For example, NASA does these calculations, and there's a big computers, not computers like our computers, like the laptops, that are able to do it. So, like I said, my objective is to utilize MATLAB or any other computational tool to be able to find a method that marries accuracy with shorter computing times, to be able to do it quick in any home computer. And there. The method that I'm following is, if you think of it, is quite simple. This is the initial equation that I was talking to you about. We introduce a multiple angle identity and some Taylor series approximations. As you can see here, there's a term called term n. That term corresponds to the order that we want to have the approximation to. So, for example, if we want to have a very accurate approximation, we'll pick a higher order, like say 15th or 17th order. And if we want a not so accurate approximation, we'll pick a third order approximation. Then in the Taylor series, we truncate the Taylor series to the order that we want the approximation to. So, for example, here it's truncated to the 7th order. Then we introduce some substitution. For people that are following, you need to have this substitution introduced in there. And then we find a polynomial in terms of x that is equal to the eccentric anomaly, the uppercase E that I showed you before. Then after that, we get this big polynomial of whatever order it is, and we find x, we find the root of it. Then we utilize something called Sturm chains. The Sturm chains is a mathematical method that's kind of complicated, but it kind of helps you tell whether a polynomial has one real root or how many real roots it has. Once we find that the polynomial has one real root that we can work with, we later introduce a generalized Newton-Raphson correction. This is, we have to introduce this because the result that we find from here, from evaluating the variable x, from finding the root, is not going to be so accurate. So we need to have some corrections introduced in there. And then we have another correction here to offset the worst error from when n equals 5. Just reminding you that m is the angle, it's a mean anomaly. We substitute this back into the original equation. We find e. Remember that this big polynomial was all equal to e. And this is what we're actually trying to find, that big E, the eccentric anomaly. So if you look closely from the past slide, how did I get from having a polynomial of such a high degree and then just simply finding the root of the polynomial? That seems like kind of hard, right? Because it's long polynomial, you can't just like go ahead and find the root like if it was a normal second degree polynomial. So, sorry. The way we do this is through, we truncate the polynomial, and then we use these Sturm chains to show that the polynomial has a real root, how many real roots it has. Like for example, I found in my research that the polynomials of the 5th, 9th, and 13th degree actually could have two real roots. And this was actually not good, because then what would happen is that we wouldn't know what to use at that point. So we needed to work with the other polynomials. Those are the 3rd, 7th, and the 7th, and the 11th, and the 15th degree polynomials. So if we go forward, this is the actual result that I get from my research this summer. It is basically an error mapping. This is using a function in MATLAB called mesh. In the vertical axis, we can find a logarithmic scale of the error. So, for example, here you can see with this scale that around the error we get is around pretty much to the 10 to the negative 15. This is pretty good, but like I told you, there's better approximations out there. Now, I suppose my research is kind of successful because we were able to do this in my laptop, like very quick. Everything was produced in my laptop, so this is more or less the objective of my research. And here we find in the y-axis we find the eccentricity that I was speaking to you about, and the mean anomaly, the normalized mean anomaly. what we do pretty much is that we loop both of them, we store it in a large array, and then we find the error for our method for all those different values. Of course, I mean, my research is not nearly done, so in the future I would like to investigate the proofs for Sturm chains and actually prove that polynomials could have one real root. Like such high polynomials could have one real root mathematically. I would like to prove it analytically, like on paper. And then I would also like to replicate the same work on hyperbolic orbits. For those that don't know, hyperbolic objects in orbits are, say for example, think of does anyone remember the comet Halley? It's a comet that passes around like 75 or 76 years, something like that. And it has no one really knows like where it goes or how it goes up to, but when it gets close to the Earth, it kind of goes goes like that, right? And you just never see it again. That's pretty much a hyperbolic orbit. Would like to replicate the same research, and I'd like to get some data for the time that it takes to compute the error and the accuracy of our method, and compare everything. And this is pretty much my presentation, I believe so. And acknowledgments to my mentor, Dr. John Presides, and the CSTEP staff and classmates that have been with me along the way, and of course Johannes Kepler for couldn't have done it without him. So thank you very much. Any questions?
I'd like to go through a few questions.
Yep.
You said that you want to reduce the computation, the amount of time it takes to calculate these functions. How important is coding efficiency to that equation versus just having a faster processor?
I'm sorry, would you
with there are certain, especially with MATLAB, there are certain ways you can reduce the amount of time it takes to perform an action, even though while performing the same exact action. So, how important is that step? Is coding efficiently? How much does that affect your reducing computation time?
So basically, this question is that. In the program that I'm utilizing, MATLAB, you need to code, you need to program all of this. So there's good ways of programming, fast ways of programming, and slow ways of programming. If you do it the right way, you'll get a very fast process. If you do it the slow way, the computer will take more time calculating things. So actually, yes, it's very important. I am actually trying to, I knew some MATLAB before coming into this research, and I'm learning a lot actually through this research, and I'm trying to learn functions and different methods of doing things in order to be able to shorten those things, because the whole purpose of the research would be annulled if my programming was faulty, so that I have to have a good programming practice in order for my results to be valid, right? So
you said why is direction negative 15 not good enough?
Well, I'm not saying it's not good enough. It's actually very good. But I'm just saying that there's better methods out there. There's more accurate methods out there. The only thing is that these methods take a long time, and that's it, pretty much.
So, you have an error of 10 to the negative 15 is important because, I know you want to put more satellites up there.
Right.
Right? So that would reduce the amount of, the chances of it actually crashing into each other?
Yep.
Okay.
That's the whole reason we wouldn't like the satellites to be, they cost a lot more. Yeah. Any more questions? Okay, thank you.